So we example, okay? And what we don't like about this example, we're going to make it messier, okay? And we're going to try to see how we can do this messy stuff in a somewhat organized way, okay? So the trouble here was that we had a predefined course list. And we know this was predefined in our code because in the code I just added in some courses and that was hardwired. Okay, so if I want to add a new course, change the number, I have to go to the program, recompile it, and so forth. Okay? So what I'd like to do now is fill this information interactively. We're going to have two phases here. We're going to first have a phase where we go, and this is very simplistic. You want a real database here, but I'm doing a very simplistic database here. We're going to have a phase where the user goes and enters some courses, okay? And then a phase where they go and search for the courses they've entered, okay? And these two phases are going to be separated with a dot. So before the first dot, you're filling in courses, and that's the interesting part now in this, for the rest of the 45 minutes we are here. And this stuff we know how to do already, okay? And if I was to show you this output, this input and output, can you figure out how to enter courses? Figure out the rules? So if I want to enter foundations of programming, I would go and enter what? Yeah.
I'm not quite sure what the RC and S is.
So this is.
Oh, regular. Okay. But if they're not a dot, then you test with RC or FS, ready for some professional seminar, and create an instance of that, and you fill in copies.
Okay. So not only are you telling me how a user should interact with it, you're even telling me how the program should be written, without my telling you a word almost. Except that somebody will tell you that RC is these acronyms. As you know, my variable names are very long. Okay, so I'm not a big fan of acronyms, but it's just that my slides cannot have very long names because they become too big. So that's why I'm using these things. Okay, so you kind of have figured out the format that if you are going to enter a regular course, you must first enter the string RC. Then you can enter. This has to be RC, right, or maybe lowercase RC, but some variation of that. Just as it has to be move or say in your assignment. And this can be any string, okay? This can be any string. We don't know it's computer science or history. That's something. And after that should be an int. And if it's a freshman seminar, you've got just a smaller set of rules here. So I didn't tell you anything, and you were speaking this language already. Okay? And when you learned English, for those of you who are native English speakers, that's how you learned it, right? People started speaking to you, and you picked it up. And you were 3 years old and you were speaking. Okay? You didn't learn any formal way you didn't learn it formally. Okay? But we're going to go and analyze this stuff to death almost. Okay? We're going to define this formally. And because we're going to do this formally, we will have a formula to go and process input like this. And that formula you can use in your next assignment. When I told you guys to parse these two commands, I gave you only 2 commands to parse, right? I could have given you many more commands to parse. And you guys already were sending PARSER messages. How can I do this cleanly? I mean, this is a mess, okay? It's okay to make a mess when you have a small amount of mess, right? So now we're going to have many more commands, so we want to do it in an unmessy way. And to just do it in an unmessy way, in an organized fashion, I've got to be a little more formal, okay? And so I'm going to give you basically, like I said, a formula. Okay. So what I'm describing here is what property of, I'm describing the input syntax, right? And what might have you heard of outside computer science, outside this course, as a means for formally describing syntax? Grammar. So we're going to do grammars. And where did you guys study grammars? I'm curious. If you studied maybe French or some other foreign language, you studied grammar. But did you guys, when you were, I didn't go to school in this country and not in your era, So where did you learn grammars, if at all?
Elementary school and then foreign languages.
Foreign languages in elementary school? Okay. Sorry?
Linguistics.
Linguistics. So, okay. So you can correct my grammar now. Grammar. So you can correct the grammar I provide you here. Okay. So here's an example of a grammar. Did you guys see any formal notation for grammars also? No? Okay. So when I studied English, we actually were given formal notation like that. Okay. And they decided that was too hard, and they start, so there was this philosophy of teaching that changed. Okay. Even when you study foreign languages, you go to a French class, the first day they just start speaking to you in French. Okay. They don't go and tell you first here's subjunctive, here's all the other aspects, and then they gradually spring that on you. Okay. So I'm saying a list of sentences is a sentence, one or more occurrence, zero or more occurrences of sentence. So this star means that a sentence list is zero sentences, or a sentence, or a sentence followed by a sentence, or a sentence followed by a sentence, followed by a sentence, and so forth. Okay. So zero or more occurrences. This is called the Kleene star. Okay. Kleene was a professor at the University of Wisconsin. And I'm saying here, now what am I saying here? You guys have already seen this kind of grammar when I just threw this at you in your assignment and explained exactly what each thing was saying. But this thing is saying?
For that example, it says if there is an imperative sentence that there exists an object.
Okay, but before you go there,
Oh, I'm sorry.
look at this one. A sentence is a
Then there's a imperative sentence or a.
or. We've already seen this symbol, or symbol, in Java, right? There's a short circuit and there's a regular bitwise and you normally use 2 bars for or, and that's a short circuit, that if the first part is going to be true, we don't have to go and evaluate the rest of the parts. And there's also a bitwise and or, where you take bits and you combine them together. And this is like that bitwise or. Okay? So saying a sentence is either an imperative sentence or an interrogative sentence, or what, something else. We're not interested in anything else but an imperative sentence for now. Imperative sentence is a transitive verb, object, or it could be, so that's what we'll declare to be our imperative sentence. By the way, the natural languages are not very amenable to these nice, clean grammars, okay? So you always do some approximation. And my transitive verb could be study or play. My object could be grammar or tennis, okay? So I'm giving you rules now. For somebody who hasn't spoken English, who doesn't have time to go and spend 10 years here and figure out all the various vocabulary, this is formally telling them what is legal and what's not legal. Okay? And so let's go and figure out what's correct and not correct according to what I've presented here. Okay? Study grammars, is that an imperative sentence? Play tennis?
Yes.
The syntax is right. That's why they talk about syntax and semantics. Okay, it might make no sense semantically, meaning have no meaning, but syntactically it follows the rules. Right? This maybe semantically also makes sense. And is that a legal sentence? No. Okay? Not at least an imperative sentence. Okay? So that's the kind of grammar we're going to be having rules like this. Okay? Now, notice some things are in angle brackets and some things are not in angle brackets.
It's like, kind of like a Mad Libs. We've got things in angle brackets like a blank, and that's what we're built underneath the blank. Put something of this kind.
So within angle brackets is a placeholder. It's a blank that has to be filled in. This is not a placeholder. It's just literally this. Okay? And how do we know what can go in here? It's defined. So this is also called a terminal. And this is called a non-terminal. Why? Because this study, you don't have to go to another rule to figure out what this is going to be. This is literally study. To figure out what this is going to be, you have to go to some other rule where this is the left-hand side of that rule and derive that, some terminal. So this is a non-terminal that has to be terminated by following some other rules, which will tell you what exactly are the terminals. Ultimately, you'll end up with terminals here, right? Ultimately, these are the non-placeholder, the terminals, and in your project, you would call these things what? Also starting with T? Tokens. So the non-terminals are the terminals are the tokens, the non-terminals are legal sequences of tokens or partial sequences of tokens. And basically these things are sentences. I'll talk about this sentences and that's right? These are sentences that are derived from the grammar. And so any sequence, and each of these terminals is the set of all terminals, the set of all words in English, you would call some of us know bigger sets than others because we have better vocabulary. Okay, the set of all terminals in grammars, whether they're English or French or computer science, program grammar, is called the vocabulary. Okay, and the sequences of vocabulary words are called sentences, just from English, and there are some legal sentences, some not legal sentences. Okay, so what we've got here are 5 sentences, one of which is illegal, and the rest are legal. Okay.
You said a set of all terminals is the vocabulary. Are you counting study grammars by tense as 4 terminals, or the combination?
So I'm counting the set of all terminals. What are the terminals?
Study by grammar.
Not sequences or terminals. So it will be the set of all terminals. Set of all sequences of terminals is the language. Okay. I know you guys are writing, that's good for you, but I've got this stuff written later too. Okay, but go ahead. When you write things down, it goes into your brain also. Okay.
So the terminals don't have to be a determined variable.
So the terminals are tokens. Variables are programming language issues. These grammars, I'm telling you, arise in all contexts. And we might even try to build grammars from the English language, like I said. Okay? So there's no variables there. They might not even, we're trying to understand what the input is. Yes, ultimately we are computer scientists, we want to parse the grammars. And then we have to talk about variables and what is stored in variables. For now, you meant variable meaning, this is like it varies?
Like it's just the simplest form.
Simplest form, terminal, primitive value, if you want to think of it that way. Okay? Okay. This is terminals versus non-terminals. Terminals are things that have arrows going into them. They don't have arrows going out of them because non-terminals are something that will lead to terminals. And so we follow some rules. And the rule says that an imperative sentence is a transitive verb followed by an object. Then we follow another rule. Transitive verb goes to a study. And so this is the study grammars is what can replace an imperative sentence. We know this is a placeholder. We need to know what this placeholder can be replaced with. It cannot be replaced with any legal sequence, any sequence of terminals. And this is telling you the legal sequence of terminals, the phrase that can replace this placeholder. Okay? So that's a non-terminal, terminal. And so terminal is a token produced by the scanner, or if you're looking at your Word document, you notice that there are 2 kinds of checking that is done. One is the spell checker. The spell checker is finding all the tokens, figuring out that the token is spelled correctly, it's really a word in the language. And then there's the grammar checker that tells you this sequence of correctly spelled words maybe have a problem. Okay? So a terminal is a token that's produced by the scanner, and instead of all terminals are vocabulary on which the grammar is based, and non-terminal is a placeholder for a legal sequence of tokens. And have you guys seen something like this when you were studying an if statement or a while statement telling you the syntax? Okay. I'm using basically the same kind of concept. And I haven't told you what a Boolean expression is. There'll be a separate rule to tell you what a Boolean expression is like. Okay. But if you know what a Boolean expression is like, if you know what a statement is like, then you know that an if statement has this form. Okay. So syntax is something we describe in programming languages and natural languages in many contexts. So else is the terminal. That's literally what you have to enter. Okay? Boolean expression, it's a non-terminal.
So what's the difference between vocab and language?
Vocabulary and language.
I know you like define both, but what's
So the language is sequences of, actually I don't define language in here, but think of language as being a sequence of legal sentences. Okay? So there's a language, there's the set of all terminal sequences.
That makes sense.
Okay?
Or that are legal.
Yeah. Well, you know, and I'm actually right now, as I'm thinking about it, there's also got to be some set of all sentences, right? I don't know what that set is called. Maybe that's called a language. Okay, but it makes sense intuitively that language is the set of all legal sentences. So I don't know what that set is called at this point. Okay. Okay, and is there a language being described here also? Okay, we'll just use this definition, that's a set of all legal sentences. We've got each program that processes input defines a grammar essentially. It's got a syntax, right? If it's reading input from the console, it's got a syntax for the input. It's implicitly describing a language. In fact, the compiler is just a program that has got a very sophisticated language that it accepts. Okay? So we, in fact, have defined a language here also, our own language. Okay? And what are the terminals now in this language? What are the tokens? So let's go and look at this. What kind of tokens are these? What would you call them? What are the rules for this? Any string. Right? We could have checking that it's, you know, some legal department, but this is just a vanilla string. So that's just as you have word, and then you can have the move command. So this is just a vanilla, it's not a word, it's just a string. I'm going to make a very simple, I've got a very simple scanner here, okay, because I don't want to write a specialized scanner. So this is just an arbitrary string. And this is going to be an arbitrary, okay, so that's my token. And RC is going to be the string RC. It's like the command move. Okay? So think of our token, think of some tokenizer that's giving you this classification. Arbitrary string, the string RC, the string FS, and arbitrary. Okay, so that's what we've got. You guys can do this again in your sleep by now. Okay? We want to go and see what kind of grammar we can build to describe the set of legal tokens. Okay? So try to, you know, I'm going to do that in the next slide. So let's take an attempt here. What are some rules you can describe here? Yeah, James?
There are three kinds of sentences, those that start with RC, those that start with FS, and those that start with purity.
Okay, so
If it starts with RC, then it should be followed by two strings and an int. If it starts with FS, it should be followed by two strings, this is the period.
okay, so what you just said was that there are three kinds of interesting terminals. Okay, there are many terminals, but three of them you found interesting: RC, FS, and dot. And you found them interesting. Why didn't you find intro programming an interesting token? So it doesn't help you make a choice. Okay, so these three symbols, these three tokens help you make a choice. And the choice you make when you have RC is that you're going to recognize what kind of non-terminal are you trying to recognize there? Give it a name. So you said RC should be followed by a string, followed by another string, followed by a number, right? Together these things denote in the abstract what? The syntax of a regular course. So RC will tell me, so that will be my non-terminal. Okay? And my non-terminal regular course goes to the terminal RC, followed by a string, followed by a string, followed by a number. Similarly, I have a non-terminal called freshman seminar, which has got a little, which is just a regular course, except it doesn't have that number. Okay? And uniting the regular course and the freshman seminar, what's something on top of that? Course is, okay, so course is either regular course or freshman seminar. Very good. And uniting courses, the dot is going to be used for what? End of a course list. Okay? Here's my grammar. Okay? My course list is a sequence of courses, 0 or more. A course is either a regular course or a freshman seminar. Again, I'm using abbreviation just to save space. So this is within angle brackets. The angle bracket regular course is either a regular course token, followed by title, followed by department, followed by number, freshman seminar. Title is just a generic string. Let's assume our tokenizer will tell me it's a generic string. Department is a generic string. My number is just a generic integer. Okay? That's my grammar. Okay? Okay, now let's use some terminology here. Okay? So in general, you have these rules and they're called productions. Okay, so whenever you have this arrow here, you're defining a rule, and this is sort of just as you have an assignment, with a left-hand side and a right-hand side. You have a rule with the left-hand side, that's a technical term, and a right-hand side. Okay? And this is alternation, okay, which we already knew. Star is repetition, which we already talked about. And RC and FS were interesting, and this dot here is, of course, just a terminal. RC and FS were interesting terminals, James, because they were used to make a decision, and they're the first symbols, first terminals in a production. Okay, so the first of a right-hand side is called the first. Okay, and that's a special kind of terminal because that helps us make decisions. Okay, so RC and FS are the first terminals, and first will be used in alternation. And I call course list a root. A root is a non-terminal that, how do you define it? Creates multiple sets of non-terminals. So why is RC why is course not a root also? It creates multiple sets, RC or FS.
But it only has one set.
It has one set at a time. So you're saying anything that is a list is a root?
One course has only, one course is either RC or FS.
This is the collection of courses.
Yes.
Would you call any collection as a root intuitively? I mean, I haven't told you what a root is. I'm telling you to define one, and you've got a definition, Fred.
I guess the root is the non-terminal that's the least terminal.
Is a non-terminal that?
It's sort of the least terminal.
The least?
Yeah.
Meaning?
Meaning that it has the most successive non-terminals leading up to a terminal.
It has the most or least?
It has the most successive non-terminals.
Okay.
Leading eventually to terminals.
So even course will lead eventually to terminals. But course list is, some course list is going to also lead to longer sequences of terminals, you're saying. And the longest sequence is the root. That makes sense. Is there a simpler definition you can give that is just, yeah?
That be just the originating non-terminal. So this starts off with course list and then goes to terminal.
So it's the originating non-terminal. And we know it's originating if it appears on the left-hand side but does not appear in the right-hand side. My course appears both on the left-hand side and on the right-hand side. So the one is a root, right? There's no arrow leading into it. So we have terminals that have arrow leading into them but no arrow leading out of them. We have non-terminals that can have arrows leading into them and out of them. And then a specific non-terminal that has no arrow leading into it is the root. Okay? And Oh, I do have language defined, and I'm glad this, but a root, we've defined sentence, any sequence of terminals. Legal sentence, a sequence of terminals derived from the root. Legal phrase, a sequence of terminals derived from some non-terminal. Okay? So that's a legal phrase. That's not a complete sentence, but it is a phrase. Language, a possible infinite set of legal sentences. Okay? And parser is a program that recognizes a language. Okay? That goes and tells you, given a sentence, tells you whether the sentence is in the language or not in the language. And it will also tell you maybe give you some data structure that represents the sentence. Okay? So when you guys did your commands in the previous assignments, you just went and executed the commands when you parsed them. Now in the current assignment that you're doing, I say, please return a command object. So I'm actually, after parsing, I'm returning a data structure that represents what you parsed. Okay? And you'll do even more of that in the next assignment. So that's what a parser is, and we're going to worry about how to write parsers. Okay? And you've already written parsers without worrying about how they're written. Now we'll worry about how they're written. Okay? So, my parser, its input will be what? In general? Strings in this case, but they were not all strings, right? Some of them were ints. So I can do it that way. I begin with strings and I would convert them into integers. And you guys have done that, right? Converted strings into integers, and you call that entity what? So you've taken strings and you've broken them into words and numbers and that scanner. We've worried about scanners already. So we'll assume a parser, we'll assume the existence of a scanner. Okay? And the output of the scanner, the input of the scanner is some input stream. And the output of the scanner is a sequence of tokens. That will be the input to my parser. Okay? So people confuse scanning and parsing all the time. Okay? And this parseInt is just this awful term for what parsing does. Okay? It really scans the string into a number. Okay? And people get confused by that and think scanning is parsing, but it's not. Okay? And parser is going to produce, either just do its thing or produce a data structure, which in general will be a tree. Okay? Because the grammar starts with the root and it's hierarchical, the data structure that you create also tends to be hierarchical, and we'll call that a parse tree. And then the output of the parse tree can be fed to an interpreter, which can interpret it, or given to a compiler, which can take the parse tree and generate code from it. Okay, that's exactly what's happening when you guys run programs. Okay, so parsing is not the same as scanning, even though in my example I'm going to combine that also just because the example is so simple. Okay, and just to show you, here is my input stream, and it's got these sentences in it. Okay, and my scanner will produce these tokens out of it. Okay, play, tennis, study. And my so token stream is the input to the scanner. Is the output, this is wrong. It's the output of the scanner and the input to the parser. Okay? And there is then a parse tree that is the output of the parser. Okay, so I might go and take this and say the sentence list, imperative sentence, transitive verb, object, and so forth, and build this tree structure just the way I've shown it. Okay, so we have the input stream, the token stream, and the parse tree in here. 3 different concepts. Okay. Okay. Questions? Now, when you're scanning, as you know, there is the input you've consumed and the input you have to consume. And my rules said, please don't go and visit a character more than once. Don't scan the character more than once. Don't do charac more than once. Okay? So you have to keep a pointer when you're scanning and saying, this is where I have what I, and so at this point, we have scanned these 3 tokens and we are about to scan this one. Do you have to keep it, and you guys have done this, right? You've written a parser, and it was not such a disorganized parser. It did its job. Did you have to keep any pointer within the token stream to know this part I've parsed and this part I haven't parsed? You did, right? You went to play, and then you went to move, and then expected some values, and then you said, okay, now I'm at say, I expect this kind of thing. So there is similarly the notion of consumed tokens and unconsumed tokens. Okay? Unconsumed tokens correspond to consumed input. Okay? There are 2 sets of pointers here. Okay? And that's something you'll have to keep track of, because I'll talk about consumed tokens and unconsumed tokens when I talk about the parser. Okay? Questions? So from this data structure, I'm going to create this kind of parse tree. Okay, my job is now that we understand parse trees, I've got this input. My job is to create a course list that consists of, actually I could have gone down to another level, but gone down to a bunch of courses, and each course can either be a regular course or a freshman seminar. So my job is to basically create this particular tree out of this. So I'm formally describing our task. Okay? That given this input, given the grammar, my job is to create, at the end of this, a course list that somebody can search later. Okay? So I told you there are 2 phases. One phase is when I enter the input. The second phase is when I do searching. In the first phase, I'll create this tree. In the second phase, I will search this tree. Just as a compiler, in the first phase, create the parse tree. In the second phase, generate code from the tree or interpret it in the case of interpret. Okay? So I'm just trying to show you in this simple case the general concept of parsing. Okay? And what I'll do, I made all these slides in the last hour or 2, so a lot of errors here. I won't have a separate scanner object. I'll just use read string and read int, which are things that I've got in my library routines. And I will go and use them to produce my tokens. So I will actually produce tokens as I'm parsing. In fact, I won't create all the tokens first and then do the parsing like I'm asking you guys to do, which is simpler. I'll parse as tokens are produced, okay? Which is typically how parsers work. Okay? I just made your task easier. So we'll scan on demand rather than store in array before parsing. Okay? And that will tell us general rules on how to write it. So I'm going to have, things are going to change a little bit. Now let's go down to writing the parser actually. Okay? So where I had a main method with fill courses and ... the ... will remain. My change into fill courses interactively. Okay? And this is going to be my parser method. And James already told us how we're going to do our parsing. We're going to look at the input. If it starts with an RC, we're going to expect certain kind of tokens after that. If a token is FS, we're going to expect a certain number of tokens after that. So that's what we have to do. Now I could do that all in one big main method, or one big fill courses interactively method. Or I could break that method into smaller methods. Okay? And obviously we want to do the second part. We want separation of concerns within the methods also. We've seen that we can take some task and say, this class does this task and this class does this task. Now we want to go and say within a class, this method does this task and this method does this task. Okay? So can you look at this grammar and tell me how I should break up my methods? And based on that, maybe we can have some general rules for getting methods from a grammar. Because that would be great, right? I've already given you a grammar. If from that grammar you can derive your parser structure, things are easier for you. Okay? So what kind of methods might I have? I'm not going to have one big fill courses interactively method. I'm going to have that method called other methods. What's an example of a method I might have there? Sorry?
Like create an object of the change on what comes in. So like you would make a regular course for a.
Okay, so give me the names of these methods. So you're saying I'll have these methods that will create courses, will create regular courses. So you said a lot of things there. Let's say parse course, okay? So parse course will be one method. Good, Fred?
You want to parser method for each non-terminal.
So that's good. You gave me an example, parse course, and you generalized, okay? And said parse course, parse regular course, parse freshman seminar, right? And my parse course method will, the relationship between the parse regular course method and the parse course method is?
Parse course calls if
Parse course will do some checking and call parse regular course or parse. Okay, that is the key. For every non-terminal, we create a parse method. Okay, and that parse method will return a value of what type? So my parse course method will return a value of type. We have already got our objects. We know the tree we want to create. Regular course or freshman seminar, is there a type that unites them both? Course. So my parse course will return a value of type course. My parse regular course will return a value of type regular course, instance of that, instance of freshman seminar. And my parse course list will return a course list. So we've got it, right? And we'll have parse course list, parse course. For each non-terminal t, define a method, parsed NT, that returns a node in the parse tree. Okay? So this calls parse course. And in general, this is a rule that you guys just said, that if non-terminal 1 is on the left-hand side and non-terminal 2 is on the right-hand side, then parse non-terminal 1, the method you create, calls parse non-terminal 2, doing some checking before that. Okay? So you've got now a general scheme for parsing. Okay? Questions? Great.
What if you mistakenly put it into parser and get something that almost fits like the legal sentence, but not quite?
So what do we do if things are illegal? And what do I always tell you guys? For regular credit, just assume everything is fine. And if something bad happens, ultimately there'll be an exception. Somebody can catch that exception, and I will try to get into exceptions. And there you can do the error recovery. So just don't worry about illegal things. That's too many ifs there. I do worry a little bit here, you'll see. But in your assignments, just assume everything goes by magic as correct. It'll make otherwise it becomes very tedious. Okay? Okay? So structure here. And what I'm going to do now, just to make things, make sure that I'm doing things correctly. So I know that this parse course list is a method I created for this grammar production. I will go and put this grammar production as a comment just to remind myself what I'm supposed to do. Okay? And it says, okay, firstly, I know I'm supposed to return a course list, so I will go and say, create a new course list. Then I will go and say, okay, while true, I will start consuming tokens. Okay? And I will consume the next token, which is going to be my read string method, which somehow magically gets a string from the input. It says if the next token equals dot, then get out of the loop. Okay? Else, I'm going to say parse course, passing the next token to parse course. Why did I do this? So clearly, parse course list has to call parse course, right? Yeah.
you're assuming all input is correct, so you can assume that parse course is not an actual thing. So you can just say add whatever course confirmed.
So I'm assuming everything is correct, no problems, and I'll return that value. That's why I've gone and added that element. And why did I pass next token to it?
Because the token has all the information that it'll use, whatever is next to the.
So that next token could have been a dot, RC, or FS. If it's a dot, I did something. That's why I had to go and read and consume it. Okay? And now this guy has to go and further do some discrimination and say whether it's RC or it's FS. Okay? So I consumed it. If it was a certain value, I processed it. If it's some other value, I asked my call method to process it. It doesn't have to consume it though. And this is the kind of coordination you have to build between these methods. And that coordination is represented by this argument I pass. Okay? And now my parse course takes the first token there and says if it is equals fs, okay, I just assume there can be small fs or mixed case, then return parse freshman seminar, else if it is RC, parse regular course, and I am doing an extra check saying if it's neither of these two things, return now. But according to my rules, I could have just said whatever. Right? I needn't have done this check. Okay, except that this guy does require some return value. And when we study exceptions, we'll see we don't even need those. Okay? And I know I am done with time, so I'll just stop at this point and we build up this from next time. Okay, questions? So we were doing parsing, okay, and we pretty much finished parsing. Let me just wrap up. This morning I saw some question on parsing. I really didn't have a chance to read it properly. So if you still have any questions about parsing after the slides I'm going to show you, then do ask, okay? So we said we've done parsing before, and we wanted to do parsing in an organized fashion. And so far, when I've been talking about organizing your code, I've been telling you how to organize, how to figure out what the various classes are, and how to divide your code into different classes that address different concerns. And now I'm going into a class and making sure that you can divide a class into divide the class into methods properly. Okay, and we are seeing a pattern for something as complex as parsing. Parsing is a very complex activity, in fact. Okay, and we said, well, we'll start with the grammar. Okay, and hopefully, how to come up with a grammar is not easy. And first we have to decide on a syntax in our mind informally. Then we have to formally describe it as a grammar. Okay. And we did that, and we said grammars have productions, and just like an assignment, a production has a left-hand side and a right-hand side, and the left-hand side says here's some abstract idea, abstract placeholder, non-terminal, and this can derive the following right-hand side, which can consist of non-terminals and terminals. Okay, so what we did was for each production for each non-terminal, we had a parse method. Okay, and the parse method was going to return a value that corresponded to some object that represents that non-terminal in the program. Okay, so our non-terminal was the non-terminal course. Okay, it so happened that we had a data type also, an interface called course. Okay, and this parse course was returning a value of that type. Okay, and in your project, you're going to have various kinds of commands, and these types are going to be the values returned. Okay, and these methods are going to access some global variables. Okay, and those global variables can tell you where in the token stream. Remember, parser is taking a token stream and producing a parse tree. Okay. So it's going to the global variables will tell you where in the token sequence you are currently. So how much has been consumed and how much has not been consumed. Okay. Plus these parse methods can take some extra arguments, and these arguments correspond to things that a particular parse method needs to look at, but may have been consumed by the parse method that called it. Okay. So somebody called parse course, and somebody had already looked at the first token, and that was the parse course list or main method, I forget which it was, and that had already looked at the period and a token to see whether it's a period or not. If it was a period, it actually did something with it. If it was not a period, it said, look, I've already consumed it, but that's not something I'm going to go and look at. So why don't you parse course look at that? Okay. So first token is going to be either RC or FS or some error value at this point. It's not a dot. If it was a dot, my caller would have processed it, and this method needn't look at it. Okay. So this one says if I'm FS, then I'll pass freshman seminar. If I'm RC, I'll pass regular course. Okay. Else now. So this is where we ended last time. We saw this last time, and I'll just quickly go through the text. Any questions so far? Okay. So, okay. And how here I'm doing a little, I'm being a little bit more disorganized than you guys will be. I don't have a separate scanner object. I could have done it. I'm just using, since the problem is so simple, I'm just to do the scanning. Okay. My past seminar freshman says, okay, at this point I am handling this particular production. Okay, this is my reminder to me. And I know that FS has been looked at. I don't have to confirm that that FS existed. And I just need to go and read this string and this string and return new freshman seminar corresponding to these values. Okay, and that's my talk. So it's all you can see. Yeah.
There's read string automatically advance one.
So what does read string really mean? Remember, there's a stream. A stream has a pointer. And every time you go and do a read, it returns one value. You do another read. If you do, it'll return the next value. Similarly, with the print stream, if I write, it'll write at some point in your console window. If you do another write, it'll write another point. So that stream is keeping that pointer. Okay, that's what you guys were doing when you were scanning. That you were reading the input stream and you were using a read routine essentially to advance that. So there's an input stream with consumed and unconsumed characters. Then there's a token stream, okay? And this is kind of unintuitive when we do this. That means read string has a side effect. Does that make sense? Read string is a function, right? Functions in mathematics return values. If you give the same arguments to a function multiple times, they'll return the same values. That's a pure function. This is an impure function. It says, I'll read string, I'll return a value, and I'll also advance a pointer. And that's a side effect people get used to. Normally, side effects are bad, but this is a side effect that is just convenient. Okay, questions? So FS is already consumed, and it consumes the right-hand side completely. And again, this is regular course and returns a new regular course. And this time it's doing read string, and a read int. Okay? And it's just assuming things will behave properly. It's not going and checking anything. If something bad happens, well, it's not supposed to happen, and that's just way too complicated. Okay? And if you have and typically when something bad happens, ultimately you get an exception. And there are ways to catch exceptions and then say, okay, this something bad happened. Okay? Questions? So this formula I've given you is called, for parsing, it's called recursive descent parsing. And it basically says you start with some productions and you come up with your parse methods. And basically, as I said, I'm repeating this, that you look at the non-terminals in your grammar. And for each non-terminal, you have a parse method. And these parse methods call each other. And if a non-terminal derives another non-terminal, then the parse method for that non-terminal will call the parse method for that derived non-terminal. Okay, so this is the non-terminal, and in its derivation you see another non-terminal. So the parse method for this will call the parse method for this, and so forth. Okay, so that's what's happening here. And finally, some, here we're calling the scan methods in when you see terminals. Now, why do you think this is called recursive? Well, okay. Why are we calling it descend? Fred?
Descending into simpler and simpler non-terminals.
You're descending into simpler and simpler non-terminals, and we're constructing ultimately a parse tree, right? And we're descending levels down. Okay, so we're starting with the top, and we're going to the next level down, and next level down, and next level down, and so forth. Okay, and in this example, does recursive mean anything here? We're not recalling something that was called earlier. A parse course calls parse regular course calls something else. It's not as if parse regular course calls parse course. Okay? In general, things will be recursive. Okay? A statement will go to an if statement. An if statement will have a then part and an else part. A then part will be a statement. Okay? So it'll be recursive. So in your example, every object that you will have that you're recursing through is a runnable. So essentially, you're recursing down to another method, run method. So run method is calling another run method, calling another run method. Ultimately, when you go and visit the parse tree. So that's why it's called recursive. But the main point is descent.
What kind of method is
Readint is a scanning method. Okay, it's like in your example, you go and get the next token from your array. You've already stored all the tokens, and then you parse it. That's not how typically things go. I just made the job easy for you. Typically, you consume tokens on demand from the parser. The parser says, okay, I need something more, and you'll go and get the next token, and you'll scan the next token. And that's why if you have a parsing error that is really serious, you won't even scan any further after that. Don't use such terms. Parse, I call scanning. Scanning and parsing are different. Java confuses you, but you have to get unconfused here. That's not parsing, that's scanning. All it's doing is reading a bunch of characters, converting that into a number. You guys have done that a lot. We called it scanning. Call it scanning. Okay? Okay, questions? So for each non-terminal, we'll either call a parse function, or we'll call a scan function. The scan function is read string here. And your scan function might just say, give me the next token that is in my array that I haven't consumed. Okay, that might be a good method to write, in fact. That you keep an index of what you have consumed till, and have a little method that says, give me the next token, and that will just go and get the next token from your array, advance the index, and that will be a convenient way to write things. Okay? I know at least one of you way back wrote an iterator interface for the scanner, and that's a proper way to do things. And I, in fact, suggested you might do it right in the beginning, and you will just say, give me next token, and that next token will just go and scan things. Okay? So this array was just a convenience thing for you. Questions? Okay, this is just saying it. And why did I go and talk about grammars and parsing here? And many reasons. It's fundamental concept. Okay, grammars are fundamental in languages in general. If you want to go ever study a programming language, you can't understand even the syntax of a programming language without knowing something about grammars. Okay, and but if you want to know more, there are 2 courses on compilers and automata theory that will both talk much more about grammars. I've done a very superficial job here. Okay, automata theory is required, so you'll see it anyway. Okay. For our project, we needed to do it. Okay, so the question is, well, why did the project involve parsing? And one of the elements of programming well is recursion. And recursive descent parsing really helps you understand recursion, and you'll see that in your project. Okay, because you will be getting to recursive types, where runnable points to another runnable, and so forth. So, at one time, we had 2 introductory courses. You have only 1 introductory course right now, Comp 110. There used to be Comp 14 and 15. 15 was for 15 was for the majors, and the 14 was for the masses. And 14 was in a practical language, so that if you don't do any other courses, you at least know something about programming. 15 was in a functional language, and they did a lot of recursion. Okay? And you guys, if you come through 110, have probably not been exposed to much recursion, if at all. And you will see recursion in 410, but it's good to see some recursion here too on practical problems. Okay? So that's the reason.